My name's Anna May, and I'm a forester and the fourth generation in the Starker family. The Starker forest started in 1936 by my great-grandfather, T.J. Starker, and it's been in the family ever since, going to my grandfather, Bruce, and then my dad and uncle, Bart and Bond, and now me and my brother and a couple of my cousins are also involved in the business. The Starker Lecture Series started as a way to honor TJ as well as Bruce, because they're both really interested in forums for debate and new ideas in forestry. After they both passed away, the family thought it'd be a good way to carry on their legacy.
Starker Lecture Series. My name's John Nairn. I'm filling in for Dean DeLuca, who is sick today, so I can't do the introduction. I want to thank you all for being here in person and remotely. I saw 15 or 20 connected. Maybe there's more now. Oregon State University in Corvallis is located within the traditional homelands of Mary's River or the Ampinafu Band of the Kalapuya. Following the Willamette Valley Treaty in 1855, Kalapuya people were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are a part of the Confederated Tribes of Grand Ronde Community of Oregon and the Confederated Tribes of Silence Indians. This Starker Lecture Series was established in 1985 by the Starker family to commemorate the lives and professional contributions of T.J. and Bruce Starker. These visionary men were both graduates of OSU's College of Forestry. In fact, T.J. was in the first graduating class and went on to be one of the college's early professors. T.J. lived what he taught and began purchasing cut-over forest lands around Corvallis. In time, these lands became the Starker Forest, a family forest enterprise that exemplifies the very best there is in private and family forest operations in this state, maybe even in the nation. This year, we celebrate the 38th year of the Starker Lecture Series. The lectures in this series have challenged our thinking about a wide range of topics from local to global scales. Many have been controversial, generating intense dialogue about our business. All have been stimulating and thought-provoking, exactly what a university distinguished lecture series should do. The theme of the 1923 Starker Lectures is innovation in forestry. Forestry has a long history of innovation amidst challenging physical, social, and economic conditions. Recent and current technological innovations include the use of geospatial analysis, sensing tools, and artificial intelligence to improve outcomes in the woods, as well as in mills and construction. We also make changes in how we make choices through social innovations. This year's lectures will look at some historical changes as well as new innovations in technologies and collaborative work. After the lecture, we'll have a question and answer period, and I hope you'll join us as well for a reception in the atrium starting about 5 o'clock. SAF credits are available and certificates can be picked up in the back of the room. It's my pleasure today to introduce you to the speaker, Patrick Freeman, Group Chief Technology Officer of the Microtech here in Corvallis. Patrick has worked in wood products industry for 30 years with Lucidine Technologies in Corvallis, Oregon, which became Microtech after their purchase in 2020. For most of this time, Patrick has led the imaging, processing, and artificial intelligence efforts before assuming the position of CTO. Patrick was appointed as the group level CTO of Microtech in early 2022. I mentioned to be question and answers afterwards, but Patrick also said that he'd be willing to take questions during the talk if the need arises. So if you have a question, just raise your hand. So please help me to welcome Patrick, today's speaker.
Thank you, Jim. Thank you for that introduction. Good afternoon. Thank you to everybody here in person and online. Really appreciate it. Glad to be here. Get to the next slide. As John has said, I am the Chief Technology Officer at Microtech. That means that I take it mean that I'm a professional nerd, and I happen to be a professional nerd both in technology and in wood. So hopefully everybody in this room starts out that way, or by the end of this talk has ended up that way. So Silicon Valley in California, that's what they call themselves. So they refer to the Willamette Valley as the Silicon Forest because of our semiconductors. But to me, this is really where the silicon forest comes from. This is where the silicon really gets the forest. So a little bit more about me. My background in universities is Clemson and the Ohio State University. We call it the Ohio State University because we're stuck up. This also proves that football schools correlate highly with great engineering skills. I would say that your team last year has increased the value of your degree, obviously. I think that through the transfer portal, Oregon State is getting Clemson's leftover quarterback. I hope that works out for them. Degrees worth a lot more here next year. All right, enough about that. My background is in robotics. My graduate studies were in dynamics of robot simulations running four-legged robots. I am still waiting for my royalty check from Boston Dynamics with their Spot Mini. The reason I bring this up is because I love robots, and I think of the themes that we make at Microtech for the wood products industry, mainly as like wood and log grading robots, because they have a vision system, they have a brain, they manipulate things, and things happen. It's a robot. So as John said, I was with Lucidine for a long time. I've been in the wood products business for 30 years, and 27 of those years was at Lucidine. We're located on 2nd and Madison. If you've been drunk at a Peacock and stumbled, you probably threw up on a doorstep, perhaps. It's a turn of the century building. It's kind of cool. You can come see that. You come see us. For a long time, Lucidine was a startup mode. A small company focused mostly on automated vision systems and mostly in the plane. And there you see one of our scanners over here. And here's the scanner. This flagship scanner that we had there would run boards through it at 4,000 feet per minute in a linear fashion. That's about 45 miles per hour. It would take resolutions down to 8,000ths of an inch. And it's applying deep learning to multiple sensors, not just color. We're going to talk about this later as we go on. But as John said, in 2020, right as COVID was hitting, that was fun. We were acquired by a company, Microtech, who's based in Europe and dominates the market there. And Microtech is the world's leading and largest dedicated wood product scanning company in the world. And it's a beautiful place if you get a chance to visit there. It's located at the base of the Dolomites. It has a medieval town that's surrounded by high-tech industries such as Microtech. We also have offices in Venice. It's a tough life, but someone has to do it. So Venice in the Alps. And we have offices in Sweden and Finland, Germany, Rosenheim, and of course here in Corvallis and in Vancouver. So we sell products all over the world, and here's what we cover. And you're going to hear Microtech a lot. I'm here to talk about tech in logs and lumber scanning. You're going to hear Microtech a lot. And so I'm going to put a lot of shameless plugs, a lot of videos and that sort of thing. And but focus on the tech, although the shameless plugs are targeted at you students I'm seeing here because you guys rock, and we'd love to have you come work for us, of course. And isn't it great being here in Corvallis, and we have some of the best tech and robotics programs and the country's, maybe the world's leading forestry and wood science program. So we're lucky, and this is why we're here, and we'd like to collaborate with you. All right, a shameless plug number one. What are we going to talk about today? Well, we're going to talk about log scanning tech, lumber scanning tech. We're going to call what we call inline components. These are kind of peripheral systems that we also make. And we're going to talk a lot about artificial intelligence, which has made a really big impact on this industry and all industries. You've been playing with ChatGPT, you know this. Before we jump into that, I want to, this is kind of a mixed audience, so I'm just going to quickly go through the pieces of a mill. And if you haven't been in a sawmill recently, or you think that sawmills aren't high tech, you're in for a real treat. Because we go into sawmill, it's crazy with high tech. It's what we call sexy with high tech. So, and typically what will happen is a sawmill is logs come in and you're gonna buck them. Bucking is they're gonna be 60 feet long and you've got to cut them into length 16, 8, whatever, in intelligent ways. Sometimes you have scanning out there and you'll figure out there's a knot cluster here and that's where you'll cut through bucking. Then you're gonna break down the log into boards in some way. And that's done in many ways, and maybe it's better to go your logs in a lineal fashion. Maybe there's a time when they're rolling and transverse. We'll look at some scanners that are here for the different flavors of that. And then you're going to go, once these flitches, sideboards, and your main boards are cut out of a plank, you're going to go through an edger. That's going to take off the wane, the curved part of the outside, off the edges. Then this is the boards that we're calling this in the green part of the mill. That's where the boards are still wet. And then it will typically go through a trimmer and you'll be cutting off the obvious big wane and in some cases other defects, maybe big rot sections. Why would you cut them off here? Because there's more processing down the way. Well, you don't want to manhandle those and you don't want to dry them because you're wasting money and time handling that. So you've got another scanner that's a trimmer that's going to cut off these things. And then you're going to go into kilns. You're going to dry that lumber. And finally, it's still rough. And finally, it's dry. And now you're going to plane it smooth on eased edges, if that's the type of lumber you're going to do. And this is the final thing before the customer. So that's the pieces within the sawmill. I'll be referencing at times within this talk what you make out of wood. Well, everybody's very familiar with the framing that's typically hidden by wall inside houses. That's called dimension lumber. We have commons, boards that would be shelving and paneling inside. Shop parts would be doors, window frames, molding, and then engineered lumber, which this building is a great example, which includes glue lamps, CLT, plywood, that sort of thing, veneer stuff. Okay, we're going to go to log skin. So again, we're featuring the tech and with Microtech products. There are others who have similar sorts of products in some cases and with some similar technologies, but I'll use these technologies to highlight these particular machines to highlight the technology. So in the log scanning solutions, we're actually going to start with these linear scanners. And as we jump into a particular scanner when I'm introducing a new technology, that's where I'll try to show the basics of that technology. So this is what we call our Log Eye 300, and it has various sensors that can be chosen. And the different versions of this scanner have a dimension only, which is a 3D triangulation. There's also color available, and then there's X-ray, which is a 2D X-ray. So let's look at those. So the idea of triangulation is that you have a laser that would point down onto a log or maybe a board, and you have a camera at an off angle. So what happens if there's a laser line projected? This camera is a frame camera, and it's going to look at this laser line, and it's going to know that when it sees in its frame the line in this position, that's at a certain distance away. And as the height changes, the actually line is seen by a camera with a frame is seen to move into a different row. And so you can take a map, you can calibrate it and take a map of those row positions into distances from the camera. So the way that logs, their shape, have been measured in the sawmill for a long time is using this triangulation method, which you see here. And you can put those all around the log and you can get a shape of it. And that shape would include not just its diameter, you can see what's called the taper and the sweep of the log, how it's shaped, because this is going to identify, be part of what's used to optimize to fit boards within this. You're going to try to cut up this log into pieces such that you get the most value out of it. And so actually, if you're only using the shape of the log, you're only going to be optimizing for maximizing the volume out of this log with the boards you cut out of it. And so we're going to talk a little bit later that, well, even better if you knew something about that log more than just the outside shape, what's going on inside, then you can cut for value rather than just volume, because those don't always correlate. You can have many parts that are worth a lot more, but are shorter, for instance. Depends on the quality. We'll get there. So here is a 3D image that's generated from a triangulation of that log. So as again, introducing technologies as we go through here at Microtech, we're actually crazy in this way that we manufacture our own cameras. And we don't just manufacture our own cameras around sensors that we buy from someone else. We actually manufacture our own sensors as well. So why would we do this instead of buying off the shelf? It's because we look at what's off the shelf and we say, wow, we want to go faster, or we want more resolution, or we want to have a frame camera and a line scan camera built into the same silicon. Or we want more memory, or we want it to be a smart camera, and we want to put a CPU on it as well. So we've made our own cameras for years. And so we use our own cameras for this triangulation. We also use our own cameras for color. So why would you take a color picture of a log? What does that help with? Well, for one thing, there are some customers who need to document the log, and this is for paying people for the logs or for documenting for the authorities. Some volume of logs. There are many reasons, especially in Europe, why you might do this. But you can do other things with a color image of the log. So these logs have typically gone through a debarker before they're scanned. And so the debarker doesn't take all of the bark off. And if you're using just the shape of the log to try to decide if you're going to cut it, well, there's still some bark left on this. It's deforming the actual shape. And so your solution pattern that you might put within this log is going to be wrong if you don't account for the bark thickness and bark that's left. So if you're looking here, you can spy the bark on the outside of the log with a color camera, and you can see when there's bark completely missing, and you can see when it's darker and thicker, and this correlates highly. Also, this is something that we find in Canada and in Nordic countries, is you can have snow on the log. That also increases its diameter, and you want to decrease the diameter before you're trying to optimize for it. So it can detect the snow and to make a good call on the estimation of the depth of the snow from a picture. Another feature that we can add to the scanner is to the X-ray. And of course, being overachievers that we are, we build our own X-rays as well. And again, for the same reasons, we make our own cameras, more sensitive sensors, quicker because they have to go at industrial speeds, etc. So these are with photodiodes, and we make our own boards. There's the image right here. This is a heat map to density of an image of a log as it went through. What you're seeing here is the knots, and you're seeing the hardwood, and you're seeing the sapwood in the outline of the log. So why would this information be helpful? Well, you want to grade a log for quality. If it has a lot of knot clusters in it, you're not going to be able to get as many premium parts out of this log. So just a 2D X-ray is super helpful for knowing quality. So you can take all this into account. You take the outside shape, you take the inside density changes in the log and the knot clusters, you take a color picture of the outside, and you're able to say a lot more about this log and what you might want to do with it. Here are some of the features that this scanner can find. Again, it has to do with the log density, average density of the log, the clusters of the knots. There's the hardwood. This thing, top break, that's a type of defect that this happens in Scandinavia a lot, where a tree will be growing and the snow gets high, and then a moose comes up and it eats the top of the tree off, and then it grows wonky. That's actually a defect, and you can find these things because you'll see the turning of the pith. The pith is the center of the tree, and that's being estimated in this image right down here. And you can see really big, obvious rot in some species, some amount of species infection. And here's some X-ray images, outline, part detection, pith detection, and knot clusters. Any questions so far? Okay, pretty clear cut. Okay, so now we're getting to different types of scanners that are measuring the outside of the log. So a lot of these type of scanners, a log is rolling transversely, and it ends up on a carriage before it's going to go through a bandsaw. And at times they'll stop and they'll get scanned with the same triangulation method. And then you only have part of the log. So you don't see the whole thing in that case. But a lot of mills are set up so you can't go in a linear fashion, or otherwise there are mechanical limitations to having a linear scanner like the Log i300. So we looked at this and we said, boy, we'd like to see the whole log and do better than that. So we thought, why not scan the log? The log is usually rolling transversely onto a carriage. So what if we could image it as it's rolling and get the outline of the log in that manner? And so we thought, how about we can do that with stereo? And sure enough, we developed a sensor, our Log i900 stereo. And as a log is rolling off the carriage down onto the carriage, it's scanned, and it's using the feature points of the debarked log, which has a lot of feature points in it. By feature points, I mean that there's scraping marks that are unique, and there's pieces of bark still left on that are in unique patterns. So as the camera is seeing more of these, it can follow these features and it can follow the movement. And so even the board's bouncing around and rolling, we're stitching these together. It's sort of like you see online where you can have lots of people take a picture of the Eiffel Tower from different angles, and then you can reconstruct from these random images the Eiffel Tower in 3D. It's using a similar technology, but it runs in real time. So I have but before I get to the video, this is why that would be helpful. If you are looking at only this part of the log and you're assuming that it's going to make this shape, but really it's got this shape on the outside, you might do a cutting pattern that would put a part here, a board here, that you would get a terrible grade out for that part. But if you know the shape of the whole outline of it, you can put a part like this there, and it has a lot less of the outside curvature in it. So this cutting pattern would be much more valuable than choosing this one, for example. So here's a video of it as it's rolling, of it picking out the shape. We have another video of it rolling on the carriage. Let me get this. Okay, I don't know why this one's not. Here we go. So here the log rolled, and you saw that it got its shape right away. So it's very fast. And the other thing that it did, and it's hard to catch that, is that it got the shape of the log as it was rolling, and then it ended up on the carriage, and it rotated it in real time using the feedback from the stereo vision linked with the control system to turn it to the right position that the optimization found was going to be the right rotation for the cut. And so we'll see that with the next log now that you know what's going on. By the way, these views are what an operator in the mill sees. They are superimposing on the log the cuts that are going to happen to the bandsaw. I'll take a while. I'll go back and oh, maybe I can. Okay, so again, it rolls. It's got the solution right now, and now it's rotating it and using the pattern to get it to the right rotation to within a degree or two. And then it will cut it to the pattern that the optimizer has figured out in that time. Okay, so you've seen triangulation, you've seen color, you've seen 2D X-ray, and you've seen stereo vision. So again, one of the holy grails, though, is to know what's going on inside a log, and then you know everything. So as we say, saw from the inside out. And so the idea is that if you can see what's going on inside, again, you can saw not just for maximizing volume, but maximizing value. Because what you have is each board has a certain set of rules for what kind of quality it can make. How many knots can it have? What length of cracks can it have? What kind of pitch pockets can it have, if any? Does it have to be totally clear? Would be more valuable. These sorts of rules. And so a perfect optimization would get all of the defect detection. It would try every single solution. So we'll get to this a little more as we go through. So this was 2D X-ray. Of course, 3D is computer aided tomography is 3D. So this is a type of image that we get from 2D X-ray. This is what we get from 3D. So we have a video, which has actually got really cool music and it's very dramatic. So the electric drums are my favorite part. Okay, so there's a lot in process there. First, a little bit about the tech here. So you noticed in that video that it's a gantry type scanner. So that thing spins at 240 RPM, which is actually fast. It weighs, what does it say here? How many kilograms? I think it says it's heavy, and the electronics on the spinning gantry have to withstand 60 Gs. So this is quite an engineering effort to balance it, to get all of the tremendous amount of data off of this rotating thing and seamlessly. But most spectacularly, was difficult to get the lineal speed. So as you see, it could go up to 600 feet per minute with a log up to say 30 inches diameter through this machine. So one of the things that this was kind of a moonshot program for the company. And it was something that they did more than 10 years ago and hasn't been equal to be able to do computer aided tomography at industrial speeds on something this large. So one of the things that they had to do was, and I think that this is shown here, is multiple sensors are put inside that gantry in down the length of the tunnel. And so this is to get gathering speed quicker, is to have more. And so the log's moving and you're taking on multiple sensors at the same time, but it's also spinning. So the mathematics of this spiraling corkscrewing were unique. And as it turns out, the story that I heard is that one of the engineers read a paper by an obscure Russian scientist who had an office in a basement in a Florida university. And the president of the company jumped on a plane the next day and talked with them, brought him back to Italy, and they worked out the mathematics, made this work, and they were awarded an innovation award by the King and Queen of Sweden. So it's that special mathematics that went into this CT, and it's very difficult to do. Once again, if you go for a CT, medical CT, you'll be going like this fast, not 600 feet per minute and not 30 inches of wood. So as you saw in this video, the log goes through and we reconstruct the defects from the images, and then we're going to optimize. So a little bit about this optimizer. I'm not talking too much about software today, but this optimizer that we call our Maxi Cut Pro, because that sounds cool, is again, you have to give it all of the products that you make and a number value assigned to the product. An example of a product might be a clear grade and it's 8 foot long and it's worth this much. Or maybe there's some kind of knotty grade and it's 16 foot of that is worth this much. You put the whole matrix of this and it can be quite large. This optimizer has to consider all of those parts, how you would maximally place your cutting pattern within this log, anticipating what those grades would be. And it has to do that for every rotation of 1 degree. So it has to do that 360 times, this optimization. So it's massive. So what we've done at Microtech is we made basically our own supercomputers out of GPUs in order to do this. And also, you might have to redo that. It might be that you scan these, we'll get to this a little bit later in the presentation, but perhaps your CT is out in the log yard and it's pre-scanned a bunch of logs and sorted them. But now you've changed the price. Your salespeople are telling you, no, this is worth this much now. You have to redo all of the logs in the yard. And so we built it pieces into this so you can run massive simulations to redo all these and do it quickly in time for you to start running these again. My first question.
How long does it take approximately per log for this optimization?
So it can depend, but say 2 to 15 seconds or so. And it depends on the complexity of what it's doing. We're trying to speed that up. And so if any of you are working into, say, optimization with reinforcement learning or something like this, come see me after that. Yeah. Yes.
When you mentioned building your own supercomputers with GPUs, how many GPUs are you using to do that?
That's a good question. I don't know the current count. So the question was, for people who might not hear this online, how many GPUs are we using? So GPUs are always advancing. And so when this was designed, we've gone through several generations of GPUs, but we're always trying to do more. So I don't know what the current count is, but I could assume it's like in some configurations, like 8 or more. Yeah. Okay. So that's Maxi Cut Pro. Here's another example of Maxi Cut Pro. In this case, this is looking at dimension mill. And so what you're seeing here is that at a rotation of 175 degrees, this solution was worth $60.67. But if you rotated it at 85 degrees and put this pattern, it would be worth $70 plus. So that's a big difference. And you do this over many thousands, hundreds of thousands of logs if you're a big mill a day, and this really adds up. So here's again driving home that a different solution. So this is a graph of rotating through all the angles and what your value is that this is computed. And so you can see that the pattern changes a lot between these two over here. And again, it's trying, the product mix that you have in those patterns is quite different. And so this is went from 106 to say 117. So another big difference just for this, even between this rotation is $2. So we're going to look at some more ways to get value out of now. That was dimension type lumber. And as it turns out that the value that you can get out is even more, not from more commodity type parts that used to frame houses, but if you do anything special like appearance grade, the value can go up even more so. So this is true, we find in hardwood. So hardwood, you can see that this is a very tapered log. And so the shape of the parts that can fit in there is affected, of course, by the shape of the log, but of course, again, by the knots and the other defects within it. So another thing about hardwood is that the hardwood is really important. So the clear pieces without the heart are very valued. Or if you have a clear front face, your back face is only allowed a certain amount of hardwood on it for certain applications. This is according to NHLA grading, that's the National Hardwood Lumber Association. So what you're seeing here, this is a board that is hard maple, and this has gone through our CT, and we generated from the CT density image. This is a virtual board, and we colorized it based on what it's perceiving in the CT. So the CT is seeing hardwood or heartwood of a certain density, and we've colorized it so it looks like an image. And when we've compared these, by the way, to the real boards after we cut them, it's pretty good for the visual image. So what you're seeing here is an example of NHLA grading. And again, if this front face is clear, it's super valuable as long as the back face only has a certain amount of heartwood percentage on it. So what usually happens in a mill for hardwood is a human being with using his vast experience will kind of size up a log and he'll say, okay, this I think will be my first cut, the best place to do it. And he cuts into it. Now he has to decide what the second cut is going to be like, and he's going to take a board off. He might decide to take a 5/4 inch thick board. That's worth a lot more money than a 4/4 inch board. But if he knows that there's hard under there, he doesn't know how deep to go. And so he's usually going to be very conservative and only take like 1 5/4 from the outside if he's really pretty sure. And then he's going to go 4/4, because if he takes a 5/4 and has too much hard on the back, he's going to have to remand that piece down to a 4/4 and chip it. So he loses a lot of money doing that. But when you have a CT, you know exactly how much hardwood's going to be on that. So this is basically showing this piece right here. He knows it's going to be safe with the hardwood, and so he can take this 5/4 thick piece that a human being never would. And also he'll be able to be spinning this log around to take the next cuts and doing the same thing. And so in doing this, we can find that we can even get in the high 20s or 30% extra value out of this. So this is a little transformative because we'd always assumed that CT logs would be good for big mills. CT scanners are good for big mills, commodity products, lots of volume. Well, there's so much value in slower and lower volume hardwood mills that this also pencils out for return on investment. Same with other appearance grades, like in cedar. In this case, cedar will have spots of peck that you see. Peck is a type of rock. And if you're trying to pick mostly clear or areas that don't have peck, the better that you can see those. You can work around them and concentrate them into a few pieces and get very high value. Clear cedar for using for all sorts of stuff for shop grades is very valuable. Again, you can choose to find those in these sections, and a human being on the outside is not going to find those. Douglas fir, a lot of people will try to pick clear grades, and vertical grain clear is very valuable. Again, you can pick that out if you choose the right pattern and do a three-sided instead of a two-sided optimization of your head rate. You get a lot of value out of just normal logs. You don't have to buy special logs that are more likely to give you a lot of clear. You can pull that clear out of your normal run if you know where to grab it. Here again is showing, again, these images that we have here are reconstructed from the CT image like we saw here. That's a reconstruction from this type of image of density. So these are reconstructed, and you can see that we have the vertical grain pattern and the flat grain patterns in this point. So this is more about getting shop clear cuttings in an optimal fashion from this log. And again, this is just showing this exercise was finding like a 23% value increase if you're pulling a real specialty product out of Douglas fir. Same for the alder industry, which is big here in the Northwest. And indeed, we've installed a CT just in the last couple of months in Washington that specializes in alder. So you can pick out the superior grades, which have clear. And picking out, selecting for rustic knotty if you like. Again, it's up to you to value these products and it will find them. Again, this is arguing for a big value increase, 29% in this case study. In this case, again, the thicker pieces are much more valuable. This is a little bit of fun that we've been looking at recently, and this is doing virtual veneer. So veneer can be used for all sorts of things. Oh, we have a question. Yes.
You mentioned that the diameter that this can visualize is dependent on the wood density.
Yes.
What are the range of diameters that it can visualize across that?
That's a good question. It does depend. Alder is not so dense, and alder can go up. I believe the numbers, I don't want to misspeak here, but I think 25 inches is possible. It may be between 20 and 25. If it's a real dense type of hardwood, it would be sub 20 inches. Yes.
What about Douglas fir?
Douglas fir can go all the way up to
30 inches.
Yes. Good question. Okay, so virtual veneer. So what happens on many softwood species is as they grow, they shed limbs. And so as they shed limbs, you'll get the sound knots near the middle, and then they'll die. You'll get dead knots for a while, but then you get clear wood, nice clear wood. So what you're seeing here, we're virtually peeling back a log. And so near the bottom end of the tree, you're seeing a lot of clear veneers. And then as you move up, you're going to start getting some dead knots, a lot of clear, but some dead knots. And finally, you're starting to get more of the live knots as you go towards the top of the tree. And knowing this sort of information for what's going on can allow you as a veneer person, whether it's for appearance grade or for engineered lumber that's made out of laminating veneers, give you a lot of really good information. The amount of knots in it and the rate of growth of the growth rings can give you a lot of estimates based on strength. Also the appearance, you'll see what the growth rings are doing, whether the flat grain patterns are wide or narrow. We've got some pictures here. Again, these are reconstructed. These are reconstructed from the CT image and colorized. So here's like an example of 5 rings per inch. Here you see that this particular patterns had much wider growth rings and wide flat rings. And here's where the pith, the center of the tree, actually took a turn. And so the grain direction in this area would be a severe grain distortion. And maybe if you're doing this for engineered lumber and strength, that's something to avoid in that area. So anyway, that's a lot of fun that we can do with virtual pieces. So how do you use this in a mill? Well, you can close couple. It's going 600 feet per minute. You can run your log right through it, and then you can go right into your sawmill. That's one way to do it. And perhaps you're going to have one of our stereo scanners down the way to match the board. So it came out of the CT, and it's been transported, and now it's rolled onto a carriage, and you use our Log Eye 900 stereo to tell you, it's telling you what degrees it should be moved to. Well, let's match the shape that you do with the stereo with the shape from the CT. It's got a solution for you ready. It tells you where to spin it and it's in the control loop and it puts it right there and cuts it. That's one configuration. So another configuration is to have your CT out in the log yard and you have bins. And why would you do this? Well, you're going to get logs in a random order and you're going to scan them and you're going to buck them and you're going to store them in bins by quality. And in that case, you could do things like, I know that I have an order for 100,000 superior grade boards by 2 weeks from now and Wednesday. And so you want to know, you can pick out of these bins a mix to where you will mix it in with others and try to get the distribution of products that you would like in the right amount of time. So you pre-store these and you know the solutions to them and how they qualified. And so you mix a population of these together, you can get the distribution that matches your orders. So now you're not a slave to just what's coming in and making parts. If you need to make these superior parts sooner out of what you may not be able to get it in the first place with the quality of your logs. But in the second place, if you're making it right away, you're wasting a lot of other opportunities by lowering the other grades to get these few clear pieces to make this order. If you can do it just in time and you can predict what you're going to do because you've scanned it, you're way ahead of the game at making money. And so in this configuration, our CT is scanning logs, putting them in bins, and then they will later on, they're stored, these solutions are stored, and they're going to go through a log eye 300, say, and this has a 2D X-ray. And we're going to use that 2D X-ray to match which log this was when it was scanned in the yard. So maybe you've scanned 500,000 boards in log. Now you need to figure out, it has a solution. Now you need to figure out that this log that's just coming into the plant, was that when you scanned there, and to use this solution. So because it's a CT, we can pretend like we are a 2D scanner with that information and generate a 2D image and log like we get at the 300. And it turns out that the pattern of the density has a distinct pattern like a fingerprint. And we store these in a database. So here that is again, the log eye 300 has a 2D scan and it has that fingerprint. So we're going to try to match it to the database of other these. And this way we're going to match it to the log as it was scanned previously. And then we're going to use the information with the X-ray images change with the rotation. We're going to figure out how it was rotated through there. We're going to pick out the right way to rotate it based on this X-ray information. I don't know the video. I don't think the music's as cool on this thing. See. Okay, the music was kind of cool. Any questions on what you just saw there? Okay, yes.
How long does it take for somebody to master that system? I mean, they're sitting in a cockpit. Is that
Yeah, that's kind of impressive, isn't it? I go there and I see these guys operating. The question was for the Zoom people, how long does it take someone to master that cockpit situation? And I don't know, I've never asked them, but it's interesting. They tell me at the mill that the people who do best at this are young people who have played video games their whole life. Really, and they're used to getting a lot of information at once. And he's moving there with a joystick to correct things, but mostly he's monitoring things. And there was this mill that I referenced earlier that just got a CT that was installed last month up at this hardwood mill. I heard information from there just earlier this week that the feedback is that their sawmill, their sawmaster who's been there 35 years cutting hardwood, he is bested and way bested by the guy who just started 6 months ago, who's operating this stuff. And so they just install it and he's beating this guy substantially. And the reason that it's not just the extra money they're making, people like him are not around anymore. There's nobody who wants to go into a sawmill and be grading logs and deciding cuts and opening it. It's becoming a lost art. And so this is another reason why people are really trying to find ways to replace this. Not only that. Yes.
How challenging is it? Because I saw that the CT scanning happens before debarking for those surface scanners later to match up to the original CT scan of the bark log, even the fact that there can do debarkers and those aren't.
Yes,
they're not
so
gonna be standard.
yeah, the question is that if you put the log through with the bark on and then want to match it with the shape. So actually we see the bark in the CT so perfectly that we virtually remove it. And then we know the shape of the log that it would match after it's debarked and run through the shape center. That's a very good question. Yes.
Yeah, Patrick, how tolerant are the scanners to the vibration of the machines and the bumping and all the motion that goes on with these big logs dropping? And then sort of part B of that is, do those scanners need periodic calibration?
Okay, so the question was, how robust are the scanners, the CT scanner to the bumping, or all of the scanners, maybe you're saying, and if they need calibration. So we do have mathematical methods that we call movement compensation. And so we are actually doing this mathematically. We anticipate some amount of motion in it, and we are adjusting for this. And so you're right, that it's not as much vibrations as it's just physics of moving things, big things really fast, and things happen. So you're right, we mathematically are, because we're sensing at multiple points, we're able to kind of reconstruct this movement and adjust for it on the fly. Yeah, we have some really good mathematicians at Microtech.
At least on the appearance side, it feels a little bit like that the standardized grading systems are pretty antiquated given the technology. So is there a future where these grades no longer exist?
That's a great question. So the question for those of you online was that we have an antiquated grading system. And is that relevant in today's world? And I've been in a cut-up plant, secondary manufacturing, that is a chop optimization plant in Red Bluff, California. And I've heard this for 25 years, and I still hear it now, is that the shop lumber grading is based on, you imagine a certain number of kind of clear parts of standard door and window frames being put in, and you have a one shop, two shop, etc. These are not relevant to all the products that are made today. And so what the person who worked in the secondary manufacturing shop wants is he wants grades that are relevant to what he does. And he would like us to optimize. He would pay more for a batch of wood that was optimized more to what he and his customers really do now. So I see this as you say, a niche market. People who have systems like this can create these custom products that they can sell their customers, and they get higher value. The customer will pay more, they get higher value. Really good question.
So,
Yes.
so you're saying basically a new grading system which is outside the official lumber grading rules, which is maybe not good enough for selling, but you could use it between window and buy. What are you saying?
Yes, yeah. The question was, this would be a new system of custom grades that you do. And these are allowed, like within commodity dimension lumber scanning, you have to follow the rules, but you can still make your custom products that you sell to someone, and that's allowed. And so the trick is you want to pull out these custom products without reducing the quality of everything else you make that you might sell in the commodity market. But again, when you have a system like this, you can simulate it and figure out how to keep the mix and keep all your customers happy, but deliver a higher value product for a certain niche of customers.
Patrick, can you anticipate the stiffness and strength of the lumber from what you see?
Oh, so the question is if we can anticipate the strength and stiffness of the lumber. You're talking about with the CT scanner?
Yeah, I mean, as opposed to bending it with a mechanical stress rating system, infer it instead of measuring it. Is that feasible?
Yes, so we actually do have an active R&D project to see what we have as a CT data that can anticipate strength and stiffness. So we do see inside the log, we see the annular rings. So you know the density is measured very well. And the density relates to modulus of MOR, modulus of rupture especially. We do see the grains diving, and we see spiral grain, and we see compression wood. Compression wood is log might have grown on the side of a hill, and it's shored up some lignin on this edge to help hold it up and that affects the strength and stiffness. So yes, there's a lot of things in the CT. We're still learning things more than 10 years later about what we can do with this. So
Can you actually go as far as grading lumber for structural use, just using your vision?
we're looking at that. Yes, and we'll be able to verify that because we have all the information, and then we have other ways of measuring the strength, but we can also put it on a machine and break them and test. So yeah, we're gathering data for this. Good, very good question. Yes, Scott.
Yeah, Patrick, I've got a couple of questions online, if I could pose those to you now here.
Okay, sure.
One is optimization time is always a constraint in high-speed mills. Some companies simplify the decision-making, such as looking at 5-degree increments rather than 1 degree. What kind of shortcuts in simplifying decision-making do you use?
Yeah, so the question was for these MP complete problems, the traveling sales problems, which these massive optimizations do, what kind of things do we do? We're using heuristics right now that we've established, and that's what you have to do to cut through the solution space because you can't do an exhaustive search. However, we have other projects where we've looked into using AI methods for optimization, for example. And these I'm really excited about to see how these fruit out. But yeah, we're always looking on ways to improve our optimization speed for these massive simulations. And another question?
Yeah, the other one is how energy intensive is the process? Is there any cost benefit analysis on implementing this in the value gain?
On energy, you're talking about like how much power is sucked up by the CT?
That's my guess there.
I guess we haven't looked at that, but we know that when I've been in these mills, I've thought about this a lot. They use a lot of power just generating air. There's air everywhere. That takes a lot of power. A lot of these mills have cogens, so they're burning their waste wood and generating power, even selling some back. So no one's ever really brought it up, to be honest, because it's obvious that it makes so much money for them that it's just in the noise. Yeah. Yes.
So you mentioned using your AI deep learning models to optimize these cuts. Most of the deep learning models I'm familiar with are optimized for two-dimensional images. Are you using your X-ray images to make slices and analyzing those, or are you actually building neural networks to analyze fully three-dimensional objects?
That's a good question. What kind of neural networks do we use in our CT scanner? And I didn't mention that so much because I'm mentioning it a little bit in another section of the talk here. However, we use voxel. It's three-dimensional CNNs to find the knots. And we're not just finding the knots, we find the dead knots too. There are a lot of grades in lumber to where you can have a live knot of a certain size, but you can't have a dead knot at all, or it's a much smaller size, or you have to anticipate it's going to fall out. So the neural net is finding both the dead and the live knots within the tree. Yes.
Okay, how much of this data is transferred on the supply chain? Like, basically, once you scan these logs and you cut them according to these cutting tools, you know everything about these boards. And for instance, panel manufacturer could really customize layouts based on the exactly individual features of each board. So how much is done right now and what's the future?
Okay, the question was, and the question was, how much down the supply chain do we transport this information? Because it would be valuable. That's a huge topic. And it's something that, I'm actually going to devote my next talk to is going to be in Montreal in March. And this is huge. What we actually do, and I have a video if we have time, which I'm probably going to run out of time, but it's about how we can track boards, our virtual boards from the logs all the way through the chain down to the planer mill. And we can match them all the way up. Now you can see what happened to all these pieces. You anticipated it would be make this grade. Well, did it when it got to the end? If not, why? That tells you a lot about your process in between, trying to figure out why, and then you can improve that process. But it tells you a lot. You can even trace the logs back into the forest. Now you know exactly what you got out of each piece, out of that log and out of this part of the forest. It's huge. It's a huge concept. And maybe I'll have time to enumerate on this at the end of the talk, but if I don't, I can talk to some of you after. Any other questions? All right, we'll run through board scanning because now I'm going long, but I love the questions. Okay, so we have a lot of products at Microtech. Again, we're just way overachievers, but we try to serve every market. So you'll notice that we call a line of our board scanners GoldenEye. Yes, it is named after the 007 movie from the 90s. Our founder just really liked the movie, and so I call it GoldenEye. So we have various forms, and what these are different flavors of a linear scanner. So again, like I said, whether you have a linear or transfer scanner depends on the layout of your mill. Sometimes boards or logs are moving this way naturally through your flow. Sometimes they're moving the other way. Typically in a sawmill where the lumber is green, just having covered the logs, transverse rules the day. But when you're in a planer mill, there's always a place where you're going linear through a planer and it's smoothing it. And that's a natural place for a scanner. So what the different flavors of all these scanners are doing is going after different speeds, different industries, different widths of boards. And so that's why we have different flavors of linear scanners. Some of them are for ripping, some for chopping, some for high-speed planes. We have a couple of different flavors of transfer scanner depending on your speed and your complexity of the problem. So here we have a linear board scanning example, and you can see that our feed works go up to the tunnel. Inside the tunnel, we have color sensors, so we have lights that are projected by LEDs. We're looking with the color cameras that we invented. And you see that we're projecting dots on the board, a pattern of dots and a line. Well, this line is used for the triangulation to get a contour, 3D contour of the board. What are these dots used for? Well, the dots are used for, and I have a laser pointer, which maybe I won't be able to demonstrate this because, let's see, because the battery just died. Go ahead. Okay, this might be hard to see. It'd be impossible to see for people on board. But you can take a laser dot, and if you kind of blur your eyes, you'll see that it got smaller on the knot. It's a circle and it's a oval on here, and it goes in an oval in the direction of the wood fibers. So what we're doing is we're projecting laser dots. We're looking with an area camera. We're looking at the shape. So we're getting the angle of the grain. We're also getting something that says with the length of it, about the length of the tracheids within the wood cells. This is all really good information. What you're seeing here is a color image of the board, and you're seeing grain deviation, and you're seeing also from the laser line itself, we look ahead of the laser line instead of on it, we get even more information. So we'll have some close-ups of this. But the idea is our scanners aren't just a color camera. There's multiple sensors in these scanners. Here's another zoom into that color. This is what we call our scatter channel. We have a deviation, a grain channel. This is 3D, kind of putting the 3D contour of the image into a 2D form. This is the laser dots. This is a piece of wood that you can see that these are forming ovals. And as you turn the wood, you can see that the ovals are following the grain direction. And as you get around a knot, you put it on the knot, the grains are diving, so the oval disappears. And when you're getting around the edges, it follows the grain. So this gives a lot of information about where are the knots, for instance. It also relates to strength of the board. As it turns out, there's a high correlation between the angle of the grains, the knot locations, and strength and stiffness. Again, since we're overachievers at Microtech, we built our own hyperspectral camera. This is, you break the color spectrum and in the infrared, even to the farther infrared, into smaller pieces. So instead of green just being between 500 and 600 nanometers, say, you'll split that into 100 pieces of 500 to 510, 510 to 520. And it turns out you can use those groupings of those frequencies in order to determine different things about the wood. So for example, here's some determinations of finding heart and sap from each other. It's really easy to see in a CT scan, but then when the wood's dried out, in some species, they look very similar, but people will pay a lot of money to not have to have the heartwood in it or have more heartwood in it. So here's a color picture of a board. And this is a board that has a story, as they all do. This is blue stain, which is a fungal infection, and there's a planar burn on it. This is a scatter image looking ahead of a laser line. And what you see is the blue stain's dark, and so is the planar burn. And you see this glowing. Well, it turns out that the resin within the center of a knot glows in the laser line. And one thing that's hiding under here, though, is this is a blonde ring around this knot covered in blue stain, but we need to know that that's a knot. Well, we can look at it in infrared, and we see that at this frequency, all of the natural, the biological, and the man-made stains disappear. We can see right through it. And now we can see, there's a knot. So again, we're showing our scanners, all of these. We could have an X-ray in this system. We've used radio waves as well. Some have used microwaves. This is a abstraction of the 3D form, and you can see that there's this planar burn made it lower here, and there's a scratch. So all of these sensors are fused together, and we're going to show them later in this to a neural network. So here's some more pictures, which I'll have to start going quicker because I'll run out of time. But here's an X-ray image. This is color images, all four sides. This is our laser image, all four sides. And this is our infrared image, all four sides. Here's what we call compression wood. And you can't really see it as well in the color, but you can certainly see it here. This is massive compression wood. This board is warped so much it went through the scanner funky because the compression wood makes the board warped in its shape. And you can really tell that in this sensor. You can tell a little bit from color, but not as much. It's completely transparent in the ion. But just a quick word about optimization here. We talked about Maxi Cut, but we have to optimize for these boards. And Maxi Cut is doing the optimization of the boards, but on steroids in all the solution space throughout the log. But the idea is you're trying to decide when you optimize the board for value, what can I get? So this board would be an economy board because its wane is all the way across the space deeply. But if you cut it in half, you make an 8'2" and 8' economy, and that's the maximum value you can get out. That's an example of the optimization. So we have various optimizers. This one's one for shop grading and it's finding clear cuttings within parts. This is one for shop grading, and it's trying to cut out knots and find clear pieces that will be finger jointed together, for instance. So again, we put a lot of work into the optimization as well. I'll really go quickly through these inline components, but I'm going to get to AI. So along with all these fancy scanners, we sell a lot of periphery equipment, including moisture meters. If you are in a cut-up plant trying to make CLT for a building like this, you can't have moisture pockets in wood, so you've got to have a moisture sensor. Well, Microtech, being overachievers again, we made our moisture sensor, and this uses EM waves at certain frequencies, and we are able to estimate very accurately the moisture within a board. We have what we call a thumper. So this is a thumper that measures the modulus of elasticity of a board, and this is a plunger which actually impacts the end of the board, and the board resonates. Other systems that do this will have a microphone and will listen for the frequency, and then with a formula they'll relate it to the modulus elasticity. We found that it's much more accurate, especially in the dirty mill environment, to do this optically. And so we built our own device for this. Also. Okay, that's really loud. We actually recently, we hung on a wall at the Microtech headquarters. We hung boards on the wall, and we had gotten them from a customer, and we knew exactly what frequency they resonate. We put thumpers on them, and now you can push a button, it makes music on the boards mounted on the wall. It's really cool. Come see it. Okay, we also, again, for the industry of mass timber, a lot of boards are finger jointed together. So we've made systems that inspect finger joints. So they're high-speed cameras that are making sure that the finger joints are perfect in their shape. And it's also looking at the glue, make sure that the glue is done right. We put chemicals in the glue so that they fluoresce in UV and they glow. And we can make sure that they're filled with glue in the right way. All right, deep learning, dear to my heart. So back in 2012, we took a real look at deep learning AI when AlexNet made a big splash on the ImageNet database. And so we started a big research project, and a few years later, we were applying this to wood. So for example, this is what's called semantic segmentation, as opposed to, say, object detection. That's where, in this case, this is a ground truth of parts of the body, and we're trying to learn the parts of the body, and this is what a net might say is the parts of the body. Same with bicycle parts, and the same for autonomous vehicles. Now, this problem is very similar to what you do in the autonomous vehicle industry, because in that case, you're merging different sensors, color cameras, point radars, LiDAR, things at different scales, and you're putting them all together and trying to make sense of the world. We looked at that and we said, we think that's pretty cool. I wonder if that works on lumber. And it turns out it does. So again, we're not wanting just to say that a knot is a knot. We want to say, well, this is the blonde portion of a knot. This is the red portion, and this is the bark encasement. The reason we might want to do that is that we might have a grade that says that if it's dimension lumber, we need to know the width is out to here. But if it's appearance lumber, we want to know the average diameter. So we need to ignore this part, for example. So we have many classes of knots: dead, decayed, encasement, blonde. We have teams of labelers all over the world. And these are people, a lot of them are expert graders who came from the field grading lumber manually for years. And now they're labeling because they know what they're looking at. So we have up to, I think we're up to 50 man years of labeling now. And hundreds of thousands of paces of labeled in different defect types. This is a sample of some of the defect types that we've taught these neural nets. The one I've highlighted here is my favorite from the South, called worm-eaten pitch. And that's my favorite because they say worm-eaten pitch. And I'm from the South, so I can say that. And I'm going to feature that one of these images. So let's look at some images here. So what this is saying, after being trained, is that we have a dead knot here. This is a pitch pocket, not a knot. This is pitch hanging off of this red knot, and there's the blonde knot with the bark. This is saying that these are two live spike knots with pitch in the middle, and it's surrounding the surface pith, which is the center of the tree. The thing about deep learning that's great is that it's using not just the per pixel value, it's using the context of everything in this image to be able to make a decision like a human would. And that's one of the big improvements that it's brought to the industry. Again, these neural nets, by the way, are being fed with all our channels. So we're saying if we have an X-ray, we feed it that. We have the dot laser, we feed it that. Color, everything. It gets all the channels and makes sense of it from exam. These are cases where it's trying to pick out the wane from where there's a bunch of skip. That means that the board wasn't cleaned up. We have to tell skip from wane. The board went through a continuous kiln and ash got deposited on it. A very difficult problem without AI that it's able to do. Funky knot, and it finds the knot and the bark encasement pitch. This is damage that was lifted off the board. This is blue stain, the fungal infection being detected. This is a type of decay. That's a decayed knot surrounded by white speck that went to honeycomb. Eastern white pine, there are different species here, so we've had to learn multiple different species, rough, green, dry, different characteristics as to whether it's for visual grading or for strength grading. This is redwood. We had to learn the difference between what's called fire scar and that it's not to be confused with sapwood, for example. These are bad and in different shapes. This is good. We've had to learn planar burns for appearance grade stuff, and the planar burns can take all sorts of different shapes. We had to learn that it's still called a knot if it's covered by a planar burn, but by example, these nets are able to do these problems. We can find bird's eye separate from leaf scar, separate from blonde and dark bird's eye. This is the worm-eaten pitch example. So this is what's called a canker or a cat face. This is in southern yellow pine. And every board has a story, of course. So what happened is this poor tree got slammed, somehow got damaged, pitch filled in the blood of the tree, and it malformed around this knot. And so it must be called a cat face. So we need to call the pitch to, and that's what you see here. This is pitch, the white is the cat face, but these pink are what's called the worm-eaten pitch. And what happens is when the pitch fills in, there's a type of insect in the south that will come and attack that. That's its way into the tree. And it starts tunneling and eating the pitch. And so any few of these worms makes this a really serious damage because they don't know how deep these went. So it's very weak. So we have to pick out these wormholes. Well, it turns out there's also a pineapple roller in the sawmill, and it put indentations into the pitch that look like wormholes. So there's no way we could have solved this without AI in the past. But it's able to, just by example, pick out from these multiple images, wormholes in the middle of all this traffic. And you have to be perfect on it because but false wormholes means you just turn a premium grade board into junk. So this is a montage of some pictures of detection of breaks on whole boards and knots, different species. This is the okay, well, we're not a one-trick pony. I told you about that we do 3D voxel detection in CT logs. That's what this is. This is the ground truth. And this is the probability map coming out of the 3D CNET. We look at the ends of logs, and humans right now grade the quality of a log. They don't have a CT. They'll fresh cut the end and they'll look to see the heartwood, and they'll look to see if there's stain in the sap and if there's rot, and where the pith was and any visible knots and put a grade. We can apply AI to this too on the ends of logs. We've recognized grade stamps, even if they're occluded by things. Sometimes they'll do a rerun. We just want to read the stamp instead of regrading it. This is something that's kind of interesting. Our Swedish branch has done aesthetical sorting. So this is where an AI is trying to learn what humans find pleasing and then sort it. So this is manually sorted lamellas in oak by humans, and this is the AI, what the AI is called at the end of the project. And they're hard to tell apart because the AI got it right. So the AI can crowdsource learn beauty and not just hue, but also the characteristics on the wood that people find pleasing for this grade, and there are several different grades. One more thing I'm going to highlight in AI is another type of problem that's not just detection. So this is the case where we want to know where the pith is with respect to a board everywhere on the board. So why would we want to know that? First off, what's pith? This is the very center of the tree, and it's where the tree was growing. And so there's the pith, and there's what it looks like in board form. Well, why do you need to know about it? Well, we had all that fancy AI that was recognizing knots right here. So as it turns out, we have to put them together to each other in the right way and estimate what is the volume displacement cross section because it relates to strength. This is called visual grading for strength. So again, you don't have a CT that sees inside it. You have to figure out what's going inside it from the outside. So as it turns out, if the AI called this was a knot head here, and this was a knot head here, and the pith is here, well, all of the knots start at the pith and go out. So that knot's going to form some sort of cylinder like this, and this will be the volume. But what if that same knot description of the knots on the outside, but the pith is inside? Then they're all coming from the pith, so it forms an hourglass, and that's a lot less volume. So we need to know, is the pith inside the board? Is it outside the board? Is it off the corner? That tells us how all these knots connect and put a volume. So how are we going to do that? Well, one thing that we've known is that people look at a board and they can kind of figure out where the pith is with respect to the board as it was in the log from the grain patterns. So we thought, oh, that'd be cool. I wonder if an AI can do that. Well, of course it can. And so here's some grain patterns when pith was parallel to a wide face. Here's grain patterns where it is inside. It looks easy, but these patterns are endless. And so what we found out is that, yes, we could apply CNN looking at all four sides, and we can give it a ground truth of a position for the pith. Now, the problem is there's so many, the solution space is huge. It takes hundreds of thousands, maybe 1 million examples to teach it to learn all the places, different growth rates that can happen, different things that can happen in the log. And so getting the ground truth of that much labeled data is difficult. So we took an idea out of a page of autonomous driving again. A lot of autonomous driving have done simulated environments for like Grand Theft Auto, and Grand Theft Auto knows where a car is and where a simulated person is, so it's got self-labeling. So we thought, well, let's create simulated logs, and then we'll take simulated boards from that, and we know exactly where the pith is in our simulated log, and we'll try to use that for training data and see what happens. So here's some simulated logs. And so we simulated it not just at the end and the growth rate, but we simulated its shape down the line. So the taper, the crook. And then we're going to grab virtual boards out of our simulated log, and they look like this. Now, right now, they're stick figures, though. And we're trying to emulate what would it look like if we put one of these through a scanner, and then we want to make a call, where's the pith? So we borrowed another AI trick, which last year was kind of in AI, the year of the generative AI. So we're using techniques like you might use for deep fakes to generate from a stick figure. We taught with just a few examples an AI to imagine what a photorealistic board would look like in its grain patterns. And so that's what we have here. Once we did that, we've been able to take virtual boards from virtual logs, and we've been able to, we know exactly where the pith is, and then we've used this for training. And then we've applied that to real boards, and it works. Any questions on AI so far? Actually, that's it. Any questions? Yes, we have a question.
Oh, this isn't quite related to AI, but it kind of is. One of the things we do a lot is dendrochronological research, where we look at age based on the patterns of the rings. So we can tell what the initiation year is based on the pattern of the rings. We know the tree was born, in 1880 or whatever, because you don't know when it dies. So, and the other thing you mentioned is some fire scars. So we also use that dendrochronological pattern in scarring. Do you know if anybody's using this technology to, I don't know, mine it? I guess mine this information for ecological and fire history, since you know the source of the wood?
So the question is whether or not anybody's using the growth ring patterns that we perceive from these to perceive more information like fire patterns in history or something like this. No, I'm not aware of that, but that would be great to do something like this. And yeah, the information is there, and you can train AIs probably to pick out certain patterns that are interesting or indicative of certain things that you've established in the past, for instance, or to generate just tons of data you can mine, or who knows what you'll find in that case.
Yeah, insects and disease patterns over time. I mean, there's all kinds of stuff you could mine if you get that specificity of what caused that damage, whether it's your tube-eating worms or whatever, and it would give you a historical perspective on the prevalence of those types of creatures. You can relate that to climate and all kinds of stuff.
Yeah, no, that's fascinating. What more can you use this information for? We did lose one of our AI members, our senior AI members, because she wanted to go work for a company that's trying to fight climate change with AI. And they're taking all sorts of patterns like this. And I was sorry to lose her, but it was like, okay, go save the world, fix this climate change thing before it gets too bad. So you can't argue with that. Any other questions? Yes.
It's part of our earlier conversation, but if we think supply chain, how much of this technology is currently applied from close distance in relatively controlled environment to the stands where you can definitely see from a moving camera vantage the crook, a taper, perhaps elements of knots on the outside to evaluate the value of the stands.
Yeah, the question here is, are people evaluating the tree as it sits in the forest and trying to take that into the mill and down the chain? And the answer is absolutely. We get lots of requests for collaboration on this, and we are collaborating on some of these, and this is the holy grail to track, as we have the previous question, track that from the tree into the mill all the way down to the final product. And then you know everything. You tie this into your ERP system and you make continuous improvement on what you're doing and you maximize your value to the fullest. This is, everybody's going for this. Yes,
We're gonna lose the room in a few minutes.
indeed. I can't show the video on this, but yeah, we're done unless there are more
All right.
questions.
Yes, well, everybody's been asking a question during the talk, what Patrick wanted, so that's fine. We have to transition from here to the reception at 5. I'm not sure how much time we'll have here, but if there's any quick questions to get in before we have to leave.
Do you consider the fact that composite materials might evolve to be pretty sophisticated things eventually, so that solid lumber is one output, but there's also other priorities for how you utilize the log? Could you incorporate those into the models?
Yes, so the question was, do we incorporate other things like not just the value of lumber itself, but other things that might come out? So as it turns, yes. So it turns out sawdust is valuable. People want sawdust for things and they want chips for things to make oriented strand board or whatever. It has a value. Also, if you're doing a cut and two on a board that still gives more value, there was an extra cost involved in cutting it and handling it. And you have to add that in. So our optimizers have ways to add in these sort of things as kind of a penalty for these. So you can have penalties and rewards for other things. Yes. Good question. Yes, so we have time for one more question?
Yeah.
Okay, yes.
Nobody knock at the door yet.
Online question from somebody who's in a log scaler, Pacific Northwest log scaler. I'd be interested in a wearable technology, laser camera that could be used to give the scaler gross measurements like diameter and length. Is this possible with technology Microtech has with their cameras and a lightweight wearable?
Wow, you look like a real nerd wearing such a thing. The question was into
2,500 kilograms or?
yeah, does Microtech come up with a remote where you can size up logs and stuff? So there are others. We haven't done this. Others have phone apps where you can do stuff like this. We have thought about doing stuff like even virtual reality, where you could put on some visors and look at our boards going by and you'll see grades projected on them, or look at our log and see stuff. That's kind of cool. We actually made a system where we have a projector system on the ceiling. We do project on boards what's going on, which is really cool. Call it great view. But yeah, we could come up with some real geeky things like this. I love that. Remember, I'm a nerd.
Anything else? All right. We can thank Patrick again and meet out at the reception.
Yeah, thank you.